Hello, my name is Connor Beard, and I'm going to be doing an analysis and a presentation of the Fibonacci problem and two of the ways that you can solve it. So let's get right into it. So this is the Fibonacci analysis, or analysis of the Fibonacci problem, where basically you want to find the nth term in the Fibonacci sequence. The Fibonacci sequence is, you know, it's a sequence that is infinite and repeats infinitely, and it's defined by each term being the sum of the preceding two terms. So at first, you start at 0, and the next term is 1, and those are the only two terms that are kind of preset inside the sequence. Those are the base terms. Everything else is based off of that. So 1 is a sum of 0 and 1, 2 is a sum of 1 and 1, 3 is a sum of 1 and 2, so on, so on, so on, until you get Fibonacci of n, where n is the nth term in the Fibonacci sequence. So we want to find the nth term. So we're going to be doing it with computers, with code. So here is one of these solutions. It is called the brute force recursion. This is the dumb solution, so to speak. It works, but it's very horrible on performance. I'll get into that in a bit. But since there's a base case, we can basically split up the function infinitely, theoretically, until every single split reaches its base case. So this is kind of a mix of recursion and then also a form of divide and conquer, but the divide and conquer part is kind of a minor aspect. It's more so a recursion because the recursion is what is contributing to the complexity of this. But as you can see, the base case is if it is the first two terms, 0 or 1, or it's going to return just n. Because if it's the 0th term, it's 0. If it's the first term, it is 1. And if n is greater than 1, it's going to return the sum of the previous term in the sequence, which it finds, putting it through the function again, and the second previous term in the function, which it also finds by recursively calling the function. So the idea is it infinitely splits the problem. So let's say you want to find the Fibonacci, you want to find like the second Fibonacci, the second number in the Fibonacci sequence. It's weird. For some reason, 0 is the 0th term. We're going to ignore that, okay? Yeah, so we're going to find the second term. So it's going to say, okay, the current n is greater than 1. So it's 2. So it's not going to do the first part. Instead, it's going to run the second part, which returns the sum of 0 and 1. Because it will input Fibonacci of n equals 1 and the Fibonacci of n equals 0. And since in both of those cases, n is less than or equal to 1, it just returns n. And then it calls them back to this part and then sums them together. And then it'll return that to this original function call whenever you call it. So as you can see, that explanation was a little bit lengthy, even though it was only the first term. Now, computers do things a lot faster than I can explain them, but the idea is that will ideally double every single time you run it. Which will be in this slide in the analysis. So again, I've said it so many times, but brute force recursion is horribly optimized, and it is super, super, super expensive. And this one case is no exception. There are ways to circumvent this kind of exception, usually by using something like memoization, or which is basically storing the value so it doesn't recursively call values that have already been solved before. But this solution doesn't do that, because this is the brute force solution. This is the dumb one. So how this works is every single time it goes to a higher number in the sequence, it splits the problem into two. So for every single n that you have, it basically splits the problem into two repeatedly. So it means it's running, 2 to the power of n problems. Something adjacent to that. It may not be exactly that number, It's more like n minus 2, but again, the higher n is, it increases uh, exponentially. So this is a horrible complexity. And the space complexity is bad too, because it needs to store all of these. And then when you get to the direct bottom of, like, this tree, which I'm calling it a recursion tree. I don't really know what it's called. If you line up all of those things that it needs to solve and store at that point before it puts them back up, the amount of things that it's adding is O of n. So it also has a bad space complexity. I mean, it's not that bad, but let's go into the better solution, which is called dynamic programming. Now, basically what this does is, instead of doing a recursion loop, we're putting it inside of a for loop. How do we do that? Well, first, we're going to store 3 variables in the function. One of them will store the quote-unquote current value of the Fibonacci sequence, the nth value that we have found so far. And we're going to store the 2 previous values as well. The base case is we're going to set the 2 previous terms to 0 and 1, and then we're going to basically repeatedly add those together to the current value, and then switch the values when the current value is found until this is repeated n times, and then that will result in the current value being the nth Fibonacci term at the end of all these loops. Here's the pseudocode. So just to look through it, so I just call this function Fibonacci. It's pseudocode. This is a base case, or not necessarily a base case, but this is just to prevent it from breaking. If n is less than or equal to 1, it's just going to directly return n, which is similar to the base case in the recursive function. But this time we're not doing recursion. We're going to set variables outside of the for loop, because we want these variables to save their values through each iteration. If we put it inside the for loop, then they would reset each time, and that would be bad. But here's the for loop right here. It's going to loop n minus 2 times, because after n minus, after n equals 2, that's when we actually start calculating the Fibonacci sequence, or after n equals 1, so n equals 2 and up. And at the end of this loop, when it's all done running and it's done looping n minus 2 times, it just returns the current value. And then that's it. So here's the analysis. This program is a lot more optimized and has a much better time complexity. The reason why is because in the recursion function, basically it split it up until it resulted in basically what this dynamic thing is doing in the first place. But much, much worse, basically. While that one splits it up until it's all lined up and then like pushes the result back up through the chain, this one just feeds the previous result into itself one time for each term that it needs to find. So it's not repeating any operations it doesn't need to perform. And the individual operations that it's doing are really not that bad. It's just adding a number and switching some variable values. So the time complexity is O of n, which is generally not very bad at all. This is actually the O of n is one of the fastest time complexities that you can get with this, even with like really weird hyper optimized like functions that they use. It'll still use 2 to the power of n as one of the base ways to find it with the golden ratio or whatever. And when you do anything to the power of a variable, that has a time complexity of O of n, because you need to repeatedly multiply it by itself until it reaches 2 of n. Anyways, but the space complexity is also very optimized, because instead of storing like a recursion chain that reaches the bottom, or a recursion tree that reaches the bottom, this one just stores 3 variables at most. Like in this, it'll store a few more, but the point is it's constant, and the amount of variables that get stored doesn't actually increase with the sequence number that you want to find in the Fibonacci sequence. It's better in every way, and I'm not gonna lie, I find it much easier to wrap my head around the dynamic programming approach than the brute force approach. So we're going to go ahead and actually go into a little fake IDE here that I have running. So first we're gonna do the recursion Fibonacci, and we're gonna go into two values and just kind of show. So I have a thing like a little timer here. How it works is it just detects when it detects it saves like right before the function starts, and then it saves right when the function stops in time, and it finds a difference between the two. It's not perfect, but it's a good way to generally find out. So I actually went ahead on my own time and kind of sounded out a good value that doesn't take too long, because again, ideally the recursion function doubles in length every time. So we're going to run this right now. So I have my two functions right here. Recursion looks shorter, but it's a lot worse. And we're running the recursion right now. This is the recursion one. As you can see, I'm calling the recursion Fibonacci function, and we're trying to find the 40th term. So let's go ahead and run it. So as you can see, it looked like it ran instantly, but that should be running a lot faster, actually. So it's very funny. The result, big number, it's not really important. The duration is insane. This is microseconds, which is a millionth of a second. So this is around half a second. Now, half a second doesn't seem bad, but remember, it's supposed to double every time. So ideally, if we go 41 and we run it again, it takes even longer. And it didn't exactly double. I'm sure there's compiler optimizations and, other things because it's running other parts. But it increased by almost double. We're going to go 42. And it should almost double again. And you can see it's taking even longer every time. It did. It even worse than double. Of course, it's not consistent because the way that it tells the time probably isn't the best. I'm on like a web IDE. But let's go to the optimized one real quick. Let's go to dynamic Fibonacci. And let's start at a clean 40, right? Because it's easy, So that was instant, right? 19 microseconds. And it found the same solution. Let's increase that just by 0. Let's just go crazy here, right? 31 microseconds. Okay. Actually, that would probably reach the integer limit. Try this. Look, it barely even increases. It probably does. Like I'm sure there's a limit here, but I'm pretty sure we reach an overflow error before it even really breaks. As you can see, the time is so insanely short that I'm pretty sure the time just running the other parts of the program are longer, which is funny. But yeah, you can see that the dynamic Fibonacci thing just has a much shorter time complexity. And we didn't really look at the space complexity in this, but let's go ahead and go back. We talked about it and we compared it. The space complexity for the brute force is oven because it splits it into a tree, and it gets the end branches and it adds all those branches together. And this the worst case space complexity is basically all those branches laid side by side, and those branches are going to be like the amount of tips of those branches is going to be n. So that's the maximum amount of data that will be stored at one time. But for dynamic programming, let's look. It only really stores 3 variables. This is constant. And sure, it stores some other things. I mean, it has int of I, but it's, this is also a constant variable. It doesn't really increase in memory capacity, unless if n goes higher than the integer limit, which it did, but, it's so much more optimized that we have to go to the integer limit before it even cares. And that's not really an issue with the function. That's just how integers work. But yeah, that's that's my analysis of the Fibonacci sequence. I referenced the Geeks for Geeks kind of page for this a lot. They give great resources. And this one's not on here because it wasn't exactly in my slides, but the Chrono library, I also use Geeks for Geeks in, and I really appreciate Geeks for Geeks for giving all these resources to use. But yeah, so that's my presentation, and my name is Connor Beard. Thank you for watching.